I'm very much the messenger in this talk because apart from throwing in an odd idea here or there, the actual work is being done by these two people here who are both working with me as PhD students. So Akshay Priyadarshi on the left, and he's coming towards the end of his PhD. He's on the lookout for postdocs, and if you like somebody who's into transmission spectroscopy, has built a transfer code exactly for that, and is working on demographics of transits and microlensing, and then he becomes highly recommended. And then Catherine Edmondson has just started as a PhD student with me a couple of months ago, so we talk about work they've been doing. Another student of mine, Eamonn is talking later on about updating some work on some of those complex dataset sites that we ever worked with Kepler DR25. Okay, so Scott showed this completely mind-blowing plot of the Hall of simulated Hall, obviously, of exoplanets that Roman can potentially deliver into the thousands of microlensing events with high fidelity mass measurements in the cold regime, and then of order 100,000 hot exoplanets in the hot regime. And this is the first survey that will give us, on an industrial scale, exoplanets from hot outwards. Okay? There's never been a survey before Roman that can do that, so that's completely remarkable. And it's going to forge together two communities that up till now have been highly separated, just like their planets. And you can see here how up till now transits and microlensing are separated in many different slices of the discovery space. But Roman is going to really transform that, and Scott showed this plot earlier from probably Wilson's simulations about how we're going to be finding apparently transiting exoplanets 4 kiloparsecs the other side of the galactic center. I think about that, potentially hundreds, so those kinds of distances. So absolutely incredible, and it's going to mean that we have a very high degree of overlap location-wise between microlensing and transit that will allow us to really start to knit together these two types of planetary systems. Right, so what I'm going to talk about is I've given a grand sounding name of exoplanet standard model. Now, I didn't name this, so actually when he was doing his second year Viva, where you have to pitch to a non-specialist member of staff and just convince them you know what you're doing. When he described to one of my colleagues who is a professor of particle physics what he was doing, the reply from them was, "Oh, I understand what you're doing. You're creating a standard model for planets." And that's the particle physics mindset. It's also a cosmologist mindset. It's never been my mindset, but why not? Right? So I'm going to call it an exoplanet standard model, and I'm going to define that as a model of the underlying present-day demographics of exoplanets throughout the galaxy. Okay, so those bolded words are crucial here, those two terms, galactic-wide and underlying. And the appeal of this is that the integral of the exoplanet standard model gives us some parameters that aren't just of interest to scientists, they're of interest to the public. Things like, what is the total number of planets in our galaxy? What is the total number of planets like Earth, and so on, okay? So what do we require for this exoplanet standard model? We need to be able to describe planetary architecture as a function of the various properties that it may correlate with, host type, age, location, and so on. And this then gives us a recipe for how to seed planetary architectures around the stars. It should come with adjustable models, so we can actually refine and fit it to data. And we're going to need the stars. We're going to need a prior galactic model. We're well used now to working with those. So the Besançon galactic model or SynthPop, something like that. They provide the stars around which we see the planets. And the nice thing about that is if the model gets revised, the galactic model, then it also advances our understanding of planetary demographics. That feeds through. And now some people can say, well, that's just, open to all sorts of degeneracies. Well, if that's true, that's an honest reflection of the ignorance of our knowledge. That's what I would say. So I would say this approach provides a very good way to study this problem, study this opportunity that Roman gives us to knit together transits and microlensing, but it also gives us potentially figures of merit, which cosmologists are very good at using, that are technique agnostic and easy to communicate to a non-expert. And I'm going to just elaborate on that before returning to the detail of Akshay and Catherine's work. So I really think we need to be able to pitch what we do. A number of times you have grant panels where there's, let alone no microlenses, which there's never a microlens on a grant panel. There's alarmingly often there's never an exoplanet expert. Okay. Now, cosmologists have insulated themselves against that problem very, very well, not just by somehow magically always having a cosmologist on the panel, but they also have a figure of merit which pretty much anyone can understand. The dark energy community agreed around the figure of merit from the Dark Energy Task Force, and it's a 95% confidence ellipse of uncertainties in two parameters: W naught, which is the present day equation state for dark energy, and then a sort of a linear term WA, which describes how it might evolve with redshift or scale factor. And that's just simple, right? We can understand it. It's a good cell, and yet it packs a lot of the physics. To estimate that, you have to really understand your survey architecture. You have to understand the physics, the cosmological physics that pins these numbers down. And you have to understand, all the confounding parameters, the systematics, and so on. So it's not easy to get those numbers, but once you get them, you have a basis for saying why your survey is so much better than what was there in the past. And it gets grants, it really works. So can we have something like that for exoplanets? And I think we can. Okay, if we take the view that if we take an exoplanet standard model approach and we get underlying parameters, then we can do something like, this is one example. Why not an error ellipse on the second and third terms of the Drake equation? Everybody's heard of the Drake equation. FP, the fraction of planets that have stars. NE, the number of the fraction of stars that have planets, and NE is the number of Earth-like planets per star. Now, of course, plenty in the literature say we already measured those parameters. I would argue we do not, because of the Drake equation, those are explicitly galactic-wide parameters. And it's only Roman's going to be the first attempt we actually have to measure those on a galactic context. So Roman, I would argue, is essentially the first survey that will pin down the figure of merit in a meaningful way. It's going to be essentially a step function of what we've had before. And I think we could sell something like this widely to try and fund our science, to exploit Roman and to design surveys beyond Roman. So back to the standard model. This provides a direct pathway to these sorts of very simple, intuitive figures of merit. So, Akshay has embarked on a kind of proof of concept. Can we do this sort of approach with large data sets? So we've started with a sort of imagined super Kepler. Okay, let's take Kepler-like efficiencies, but let's say we detect 10,000 systems, 10,000 exoplanets. So he simulated the properties of these systems using Kepler ports to model the efficiencies. And then we've applied our standard model, which is about as simple. We've started about as simple as possible here. So we've got a number that varies with mass ratio Q and host separation A as power laws. You might wonder why we're simulating transits with Q. I'll say something about that in a moment. Beta then is the seventh parameter in this model, which is the summed planet masses around a host to the mass of that host. Okay, and this simple model just assumes these are universal, so there's no sort of galactic sensitivity or host star sensitivity. It's really simple. So it's a very naive and simple model, but even this is like 7 parameters. Now back to Q. We've chosen Q because we intend to integrate microlensing as well as transits. Okay, and one measure is essentially radius, the other is measuring essentially mass. So we're going to need a mass-radius relation at some level to transform between these. Okay, so Catherine Edmondson, as an undergrad, worked with John Norris and myself to do a mass-radius equilibrium temperature fit to the exoplanet archive as it was then, and we didn't assume regimes. They wrote codes to do an ODR fit and work out how many regimes and what the boundaries are and so on. And it recovered 3 regimes, so that's sensible because we all know it's 3 regimes. And it also preferred that they are discontinuous, which confirmed some earlier study by Ategi et al. And we had a temperature dependency for the hot Jupiter regime. And these analytic models actually outperform the widely used cherry-clipping forecaster models, so they seem very useful for the purpose. So our exoplanet standard model uses that to transform between Q and radius. And so the process is that we use the exoplanet standard model to seed planetary systems around host stars in the Besançon galactic model. We then work out what the detection efficiency of those by basically finding the nearest neighbor Besançon star within the Kepler port's actual star sample, nearest neighbor in terms of host property, and then assign that efficiency to that Besançon star. And then we propagate through to get about 10,000 discovered, so-called discovered beds. Okay, and here's what they look like on the left with our injected model. That's the predicted versus, the period versus radius 2D histogram. And then we have a likelihood indicator to work out, so that we can then recover the underlying parameters by comparing the the period versus radius parameter space. And this is one example of recovery. You can see it's quite reasonable, slightly overshoots on the expected number of detections, but it does a quite credible job. So we think that it's actually definitely credible. It's quite time consuming. I think there can be improvements with how we handle Kepler ports. Just looking at the actual recovered parameters, they look sensible. So the truth is shown in green, the best fit shown in blue, the dashed lines show the 1 sigma errors, and so the blue is about as neighbouring green as you'd expect it to be. And for parameters where you don't expect transits to be sensitive to, such as the outer radius of planets, A2, sure enough, the posteriors say, haven't got a clue, basically. So it's doing all the right things. An update which I think we'll try. Catherine had a look back at the mass radius relation. Instead of doing it in physical space, she's done it in observable space. So this is now transit depth, mass ratio, period, and host temperature relation. And we found actually it does a really good job. And it's a much easier relationship to wield if you're combining microlensing and transit data sets. So I think this might be a better way of doing it. And it looks really nice. It has some advantages. It's not discontinuous. It's a continuous relationship, and it's quite obviously stratified in host temperature. So it looks pretty good. Okay, so in summary, we're going to get a large data set with Ronan, and I think of it as one data set, 2 different methods, but one data set. We're going to need methods that optimally combine, fully exploit both data sets rather than looking at the common overlap and working out the demographics on some common subsample. The grandly named exoplanet standard model provides one approach to doing this. It also has an advantage that I think it can produce figures of merit that are much more sellable. And its technique, those figures of merits will be technique agnostic. Our initial tests show that this is feasible. It's not easy, it's quite computationally expensive, but it is certainly feasible. We need to up the scale to hundreds of thousands of events. We need to include microlensing. We need to include an updated observable equivalent of mass radius relation, but the trajectory is all in the right way. So that's where we are, that's our update, and that's all I have to say.
So, I guess I don't follow cosmology quite as closely as I used to, but my impression is that the dark energy figure of merit is not quite as widely regarded as you seem to think. You know, and this partly comes from discussions in the early days of living first and to when it transition to the larger telescope. But I would suggest that, you know, these figures of merit, if you're working on it, you should probably, I would say, to come up with maybe different versions. And, you know, there might be ones that are sort of seem reasonable that, you know, actually give very different results about what you're measuring about the system. So, and, you know, cosmology is easy compared to exoplanets. So, you know, you can that, you know, as theory develops, I think that, you know, the things that people think are important.
I mean, I would say a couple of things. I always think we're kind of 20 years behind in terms of sophistication with the cosmology community. But that figure of merit is 20 years old. So I think we're hitting a data-rich era, and I think there's a critical mass in what we do that motivates a figure of merit to be understood outside of our community. Whatever internally the cosmology community might think of that figure of merit, it is widely used still to convince people outside the community to you know, fund surveys, to fund science exploitation, and I'm quite convinced that they have been rewarded handsomely for coming up with maybe something that's suboptimal, but something that sells. I think we really need that.
So I think this is great stuff. I encourage you to think even more ambitious.
베개 하나 줘.
And in particular,
김치.
I'm worried about is this false
야,
positive.
이거 말고 그거 줘.
Can you please on Zoom?
This false positive. So rather than an exoplanet standard model, how about just a companion standard model that includes the binary distribution as well, which you're going to have to actually fit for to figure out which fraction of your signals and transits are planets and which fraction are binaries. And similarly, really, you know, where we arbitrarily cut off the mass ratio function and say, this is a planet, this is a binary, is arbitrary.
Yeah, no, I'm all for, you know, the best figure of merit for me is one that packs the most physics, which is the direction you're traveling in, and all the cells, which is the direction that I worry about as well. Somewhere, they meet somewhere in the middle, or they optimize somewhere in the middle. This is one suggestion, and I'm not trying to pretend that I've found the optimum.
Yeah, my impression is that it's difficult to do this without oversimplifying in some way. Because once you want to put also data from different methods, so if you want to inject microlensing over Kepler, then you cannot neglect the fact that you are looking at completely different stars, M stars instead of FJK stars, and so and then you're looking at planets beyond the snow line. So putting everything together would require much more parameters than oversimplified time.
I mean, it's not as different with Roman as it is right now. And I think, if you, again, look at cosmology, they measure these parameters with supernovae, they measure it with barometric acoustic oscillations, they measure it with redshift space distortions, weak lensing, etc. They've got many different methods that on the face of it don't seem related at all, but they're all after the same goal. I think, you know, we are at a mature point now, we can start to take this some other philosophy. And I think
So in fact, they find the Hubble tension because they're mixing two.
And they'll get funding for it.